Hello everyone. Today I am going to discuss about the topic on antenna measurements. In the antenna measurements, we are going to talk about radiation pattern and impedance measurement. Before going into the topic, we must know the need for antenna measurements. The need for antenna measurement is to ensure the antenna whether it meets certain specifications or not, because if we take some examples, the applications like mobile and personal communication, remote sensing and radar, they require some strict specifications like it should have a certain gain, side lobe level, polarization, etc. So, in order to check whether the antenna meets certain specifications or not, we need to have measurement on antenna parameters. And the second need is to characterize the antenna, we need antenna measurements. In antenna measurements, the typical parameters are gain of the antenna, bandwidth, its radiation pattern, beam width, impedance, etc. So these are some of the typical parameters measured during the measurement of antennas. And in this topic, we are going to see first the measurement of radiation pattern of an antenna. We know the radiation pattern is a graphical representation of radiation as a function of direction. There are two types of radiation pattern. One is known as power pattern and another one is known as field pattern. So these types are classified based on how we are measuring the antenna radiation. If we measure the antenna radiation in terms of power, it is known as power pattern, or if we measure in terms of its field strength, we are calling the antenna radiation pattern as field pattern. So there are two types of radiation pattern. One is known as power pattern and another one is known as field pattern. So in the antenna measurement setup, we need the following requirements. They are the first requirement is antenna under test. So this is the antenna for which we are going to measure the radiation pattern. And second one is we need another antenna which is kept at some distance away from the first antenna. And the third is antenna rotator mechanism. In the antenna rotator mechanism, we need a mount which is used to hold the antenna for rotating it, and we also need receiver or detector in order to measure the received radiation, and next is the indicator to know the readings what we measured from the antenna radiation. So these are the requirements in the antenna measurement setup. So this diagram represents the radiation pattern measurement setup. So in the left side we have an antenna called primary antenna, and the right side we have another antenna called secondary antenna. So there are two methods in radiation pattern measurement. In the first method, primary antenna is kept stationary, that is the left side antenna, and the right side antenna, secondary antenna, is rotated from 0 degree to 360 degrees in order to measure the radiation which is transmitted from the primary antenna. So here the primary antenna is the transmitting antenna, secondary antenna is the receiving antenna. So this type of radiation pattern measurement is suitable for low frequency applications. And in this type, first the primary antenna is radiating and the secondary antenna is rotated in 360 degrees at constant radius, and at the same time we will measure the readings. For example, at 0 degree, when the antenna has no rotation, the secondary antenna, the radiation is measured, and at 10-degree rotation, the secondary antenna radiation, received radiation, which is from the primary antenna, is measured. In this way, from 0 degree to 360 degree at a constant radius and also at the constant degree variation, we will measure the received field strength or received power from the secondary antenna. And after that, we should use a polar plot to draw the radiation pattern. So from the radiation pattern, we can easily understand which type of radiation pattern the antenna will provide. And this is the first method. And in the second method, the reverse case, where the primary antenna is rotated and the secondary antenna is kept stationary. And now the secondary antenna is the transmitting antenna and the primary antenna is the receiving antenna. So this primary antenna, the same thing, the readings are taken from 0 degree to 360 degree. The polar plot is plotted with the readings and the radiation pattern is understood. And the first method is suitable for low frequency applications, and the second method is used for high frequency applications. So these are the two methods. The first method, primary antenna is stationary, secondary antenna is rotated, and the readings are taken with respect to the first antenna. And in the second method, high frequency applications, primary antenna is rotated and the secondary antenna is stationary. So this is the radiation pattern measurement setup. And in this, we should consider an important point that to get accurate far field radiation pattern, the distance between the primary and the secondary antenna should be r greater than or equal to 2d squared by lambda. Here r is the distance between the transmitting and receiving antenna. Here capital D is the antenna dimension, lambda is the operating wavelength of the antenna. So we should remember that in order to get accurate radiation pattern in the far field, always we must keep the distance between the primary and the secondary antenna should be greater than or equal to 2d squared divided by lambda. And in the antenna measurements, we are going to see the next parameter measurement known as antenna impedance measurement. So here also the frequency is involved in the two types. Here there are two types, two methods are there. One is the first method known as bridge method. This is for the low frequency when the antenna operated below 30 gigahertz. Below 30 megahertz. And in the second method is known as slaughter line method, and this is suitable for high frequency applications, and this method is suitable for higher frequencies, that is above 1 gigahertz. And for in between 30 megahertz and 1 gigahertz, we can use either method for impedance measurement. So there are two methods based on the frequency. For low frequencies less than 30 megahertz, we use bridge method, and for higher frequencies greater than 1 gigahertz, we use slaughter line method. And in between these two frequencies, we can use either first method, the bridge method, or the second method known as slaughter line method. So this is the diagram for bridge method. We know a famous Wheatstone bridge is used here in order to find out the unknown antenna input impedance. Here there are 4 points A, B, C, D, and there are 4 arms here, A, B, B, C, C, D, and also A, D. Here the impedance arms A, B and B, C, that is the arms which are having the impedances Z1 and Z2 are known as ratio arms. And the Z3, the variable arm impedance, that is CD, is known as variable arm. That is variable impedance arm. And A and D, A to D, the arm is known as unknown impedance arm. And this is the arm where we are connecting the antenna input terminals. So in order to measure the antenna input impedance, we should connect the antenna in between the terminals A and D. And now, so in this circuit, the Z3, the variable impedance, is varied until the detector shows null position. So this is known as the bridge balanced condition. So under bridge balanced condition, so we should know Z1 by Z2 is equal to the ratio Z4 to Z3. So under this we know Z1 and Z2 and also Z3. So the unknown impedance Z4 can be easily determined by this method, that is bridge method. And second method is called slaughter line method, and this slaughter line method is determined from the characteristics of traveling waves. That is, when there is a traveling wave on the transmission line, we have maximum Vmax and also V minimum points. So from Vmax and V minimum points, VSWR calculated, and we know that the parameter VSWR, that is voltage standing wave ratio, is equal to 1 plus magnitude of capital gamma, that is reflection coefficient, divided by 1 minus capital gamma, the reflection coefficient magnitude. So this reflection coefficient is equal to the ratio of reflected voltage divided by the incident voltage, and in other ways it is known as the formula load impedance minus characteristic impedance by load impedance plus characteristic impedance. So after finding this reflection coefficient and the voltage standing wave ratio, we can easily determine the input impedance of given antenna from the formula Zn is equal to Z0 into ZL plus JZ0 tan beta L divided by Z0 plus JZL tan beta L. Here ZL is the termination impedance or load impedance, we know, and L is the length of the transmission line, that quantity also we know, and beta is the propagation constant, we can easily measure from the formula 2 pi f divided by the Vp, that is phase velocity. So if we know all these parameters and also the characteristic impedance, we can easily determine the antenna input impedance. So this is the slaughter line method, which is used for higher frequencies. And in the slaughter line method, so this is the arrangement of slaughter line method. So this is the block diagram. There is a signal source, low pass filter, and slotted coaxial line. Antenna under test is connected after slotted coaxial line. We have a probe on this coaxial line in order to measure, and we have a detector, amplifier, and indicator circuit. So this is the block diagram of slaughter line arrangement. And in a transmission line system terminated in an antenna, we know when incident and reflected waves meet, there will be standing waves occurs along a transmission line. So a part of the transmission line is replaced by an axial slaughter line. The slaughter line arrangement is shown in figure. So here the slaughter line arrangement has a transmission line, that is a coaxial cable with an axial slot along which a traveling carriage which carries a probe. So that will be in the second diagram. So in this diagram we know there is a probe which projects through the slot, and the standing wave pattern is obtained by moving the probe along the carriage and observing the resultant variation in the crystal detector output. The probe in the selected coaxial cable is moved and Vmax, Vminimum points are noted here. And from the Vmax, Vminimum points, we can easily determine VSWR, and from the VSWR we can calculate the reflection coefficient, which is the ratio of reflected voltage to incident voltage, and from all these parameters we can find out the antenna input impedance. So this is about slaughter line method. With this we end the today's discussion. Thank you.